In this video, I'll introduce the idea of how to write an amount of accumulation precisely using the scenario of a Mars rover. As you may have seen in a previous video, the Opportunity rover landed on Mars in 2004 and has been actively exploring the planet ever since. It is powered by solar cells. As the rover travels across the Martian surface, it kicks up dust, which accumulates on its solar cells. Once the solar panels have accumulated 200 milligrams of dust, they'll stop providing enough power for the rover to move. The rover is following a 100-kilometer path. The rate at which dust will accumulate on the solar panels can be modeled using this function, where p is the position along the path, and r of p is measured in milligrams of dust per kilometer traveled. The goal is to figure out whether the rover's solar panels will accumulate 200 milligrams of dust if it follows this route. To get started, let's look at a graph of the dust accumulation function. To approximate the total amount of dust that accumulates, we'll use a left-hand Riemann sum. To start, we have to divide the 100 kilometers into intervals. We'll start by using intervals that are 10 kilometers long each. Since we have 10 intervals and we're using a left sum, the bounds of the sum will be 0 and 9. Then we need to find the rate of dust accumulation. We can take these rates from the start of each interval. And then what we do is assume that the rate stays constant for each 10-kilometer interval, which will make our graph look like this. And then we know we're using the rate of accumulation at the start of each interval. Then to find the amount of dust that accumulates in each interval, we multiply the rate of accumulation for each interval by the amount of change in position for each interval, which makes our graph look like this. So we know that to find the amount of dust that accumulates in the first interval, we multiply r of 0 by delta p, which in this case is 6 milligrams per kilometer times 10 kilometers. And then we do this for each of the intervals. And then we add these values up to get a total of 229 milligrams of dust that has accumulated. Since we're assuming that the rate of accumulation was constant for each 10-kilometer interval, the number we've computed is an approximation of the actual amount of accumulated dust. In particular, we can see that the rate of accumulation at the start of each interval is larger than the rate for the rest of the interval, which means that the number we have computed is an overestimate of the actual amount of dust that accumulates. In particular, if I highlight the parts of our Riemann sum computation that are contributing to the overestimate in each interval, we can see the amount of error in our estimate. This leads us to the question, how can we make our approximation more precise and reduce the amount of error? Let's think about what would happen if we switched from using 10 intervals to 20 intervals. This would mean we'd switch from k equals 0 to 9 to k equals 0 to 19. If we used 20 intervals that each be 5 kilometers long, then we need to find the rate of dust accumulation at the start of each interval. And we would, again, assume that the rate stays constant for each 5-kilometer interval, which will make our graph look like this. And then we know we're using the rate of accumulation at the start of each interval. Then to find the amount of dust that accumulates in each interval, we multiply the rate of accumulation in each interval by the width of the interval, which makes our graph look like this. Like before, we'll add up the amount of dust that has accumulated in each interval. And this time we'll get 213.8 milligrams of dust. Also, like before, this is an overestimate of the total amount of dust that accumulates. However, we're only assuming that the rate stays constant over each 5-kilometer interval, and not over the 10-kilometer intervals. So this should make our approximation more precise. We can see this by looking at the amount of error that came from assuming that the rates were constant over each interval. We can see that the error was less than it was before. So the way to make the approximation more precise is to use more intervals. Here we have our Riemann sum with 20 intervals. The orange part of the graph shows the amount of error in our approximation that comes from assuming a constant rate of change for each interval. What would happen to this error if we divided the 100 kilometers into 30 intervals? What about 40 intervals? Or 50 intervals? Or 75? Or 100? Or 200? Or 500? You can see that in this sequence, as the number of intervals gets larger, the amount of error gets smaller, and the value of the Riemann sum approaches the actual amount of accumulated dust. We can use the idea of a limit to express what is happening here. So, R of P is the rate of accumulation in milligrams per kilometer at position P, and we divide the 100 kilometers into n intervals. If we let n get larger and larger, and look at our limiting value of the sequence, then we'll be computing the total amount of dust that accumulates on the solar panels. There is another way to write this limit. We're letting the number of intervals in the Riemann sum go to infinity, and to show this, we turn the summation symbol into an elongated S. We write a 0 below and 100 above to show that we're adding up amounts of dust from 0 to 100 kilometers along the path. We're still multiplying the rate of accumulation by the length of the interval, but since we're looking at the limit as the number of intervals approaches infinity, we're no longer looking at a specific number of values of p, and the length of the intervals gets infinitesimally small, which we show by changing the delta into a d, like we did with derivatives. This limit, which we call a definite integral, is another way of writing the total amount of dust that would accumulate if you added up the amounts of dust that would accumulate at all of the infinitesimally narrow intervals between 0 and 100 kilometers along the rover's path.